latest interest.
Thanks. So I see that I'm already over time, and with that in mind, I'm going to do something different. I'm just going to start right at the end here and hit the most important point, which is Intel is hiring. So if you take anything away from this talk, take those last two bullets, that if you are a machine learning or autonomous vehicle student or ML AV professor, please contact me. As Raul was saying, I have deep ties at Intel on academic funding, and I oversee a number of different collaborations, a lot right now with Stanford and Brown. But if you were in my seminar last night, you know that I want to include Penn in that as well. So this is the one thing that you should take away from this talk. And now I'm going to try to give the 2-minute version so I don't steal any time from Ben. Okay, so let me give this a shot. So the emphasis of this talk is really about anomaly detection. One of the things that I do at Intel is oversee the Intel Labs BMW working group on anomaly detection. And anomaly detection is really important because we want to essentially get to the point where we're this guy, where we can just sleep in our car and everything's fine. But in order to do that, we need to be able to handle anomalies perfectly, and we need to be able to do some sort of verification that our neural networks, if those are driving our vehicles, are going to behave correctly. So those are the two things that I'm going to quickly talk about today. There's obviously lots more that we need to do to get to level 4 autonomy, but for this talk, we'll just talk about those two topics. Okay, so an example of anomalies are things like blizzards, these limping failures, pedestrians on the street, erratic driving. It can be internal and external. What makes anomaly detection really challenging is sometimes these things can be compounded. They can be compositional. So you can have a blizzard out that affects your external sensors. It can result in limping failures that affect your steering. Then there could be pedestrians on the street because their vehicle has crashed off the side of the road. And you have erratic driving because people are losing friction on their vehicles. So you can imagine trying to manage all of these anomalies simultaneously can be really challenging. Though one important thing that Intel is really trying to avoid that Matthew O'Kelly, hopefully he's in here, he mentioned earlier, is this loss of life. We really need to make sure that we're doing a really good job reducing this rather than increasing this. So there's two key areas that we've focused on improving anomaly detection. The first is transitioning from point-based systems to time series. And here you see a figure that shows, figure 1A shows a point-based system, and figure 1B shows a time series system. What we've done is we've redefined the core mathematics behind anomaly detection to be range-based. And if you'd like to learn more about this, you can look our SysML 18 paper. And then we've also introduced this thing called zero-positive learning. What zero-positive learning is, it essentially trains an ML model entirely in the negative space. What that means is it's the non-anomalous space. It doesn't train with any anomalies. This could be really powerful for a variety of reasons. The first is anomalies are rare, so the anomalies may not actually be in your data set. So you may only have non-anomalous data. So if you can train to learn the anomalies that you haven't even seen, this would be really powerful. The second thing is that new anomalies can occur without further notice. You don't know about these anomalies before they just eventually rise. It turns out that zero-positive learning is actually very well suited for this type of problem because it learns in the negative space. What we've seen is that it can learn several new anomalies that's very different from classical techniques that only train on very specific types of anomalies. And if you want to know more about that, you can look at our other SysML paper called Greenhouse, a zero-positive machine learning system for time series anomalies. Okay, so now on to verifying these deep learning systems. So the big question comes up is if we have deep learning in these safety critical systems, is it safe? One thing to keep in mind with deep learning is it's probabilistic, right? We're guessing. We don't know for certain that this is the right decision. So how can we ensure that these systems will behave correctly? One way is we can use formal verification. So formal verification will essentially do an exhaustive search through all the possible paths that you can take for that machine learning system and verify that the behavior is going to be correct in cases like adversarial data or sensor corruption. The problem with verification historically, though, has been it's been very slow. So we've tried to attack this in two complementary ways. The first is we're looking to constrain the SMT solvers. By constraining them, we can make them more performant. And the second is we're trying to optimize the DNN system. So if you have a deep neural network, there's certain changes that you can make to it that make formal verification a lot more computationally efficient. For example, if you can restrict your activation functions to rectifier linear units, that turns the activation functions into linear problems rather than nonlinear, and that can speed up the disjunction analysis that the SMT solver has to perform. And if you want to know more about that, you can look at our CAB 17 and our SysML 18 paper. So now, I'm back to the conclusion, and that only took 5 minutes. Remember, the most important point is this last one, and I should be around for the rest of the day. Please find me, and let's talk if you're interested in these areas. Thanks.